Okay, so now we're on to section 4.1. We're going to be talking about how derivatives affect uh, the shape of the graphs of functions and how we can apply these facts to a variety of problems. So first of all, we're going to be talking about maximum and minimum values. And let me just go through the definitions of these things and also some vocabulary. Uh, so first of all, if f of c is greater than or equal to f of x for all x, we say that there is a global or absolute maximum at c. If f of c is less than or equal to f of x for all x, we say there is a global or absolute minimum at c. However, we might have points where it looks like a maximum or minimum, but it's not a global maximum or minimum. So we have, for example, if f of c is greater than or equal to f of x, for x close to c, we call that a local or relative maximum. And if f of c is less than or equal to f of x, for x close to c, that's called a local or relative minimum. And just to be careful, when we talk about minimums and maximums, we're really talking about two things. We're talking about where are they located and what the value of the minimum and maximum are. So oftentimes they'll say, where is the minimum or maximum? That is the x value. The minimum or maximum is located at the x value, c. The value of the maximum or minimum, the minimum or maximum is equal to the y value, f of c. So just be careful to get those two distinguished. Okay, so let's consider the function with this graph right here. The absolute maximum and minimum are going to be the highest and lowest points respectively on the graph. So the absolute maximum occurs at x equal to 1 and is equal to 4, right up here. The absolute minimum is equal to 0 and it occurs at x equal to 2 down here. Now we also have a local maximum and a local minimum here. Right here our local maximum is 3, 2. It's not an absolute maximum because the function clearly takes on higher y values on different parts of the graph, namely over here. However, if I were to draw sort of a small circle around this point, I would see that within this local area, this point actually does have the highest y value. So this is a local maximum. For x values close to 3, 2 is the biggest that y gets. Over here, we have a local minimum. Although the function takes on values that are less than 1, at x equal to 5, this is the lowest that the function is, close to 5. Okay, so we would like to know when we can find maximum and minimum values. And we have something called the extreme value theorem, which tells us when absolute minimum and maximum values exist. So if f of x is continuous on the closed interval from a to b, then f of x attains both an absolute maximum and an absolute minimum value on a comma b. So that's something like this picture right here, where I have a function which is continuous on the interval from a to b, like this. And so this guy happens to have maximum right up here, the absolute maximum right up here, and the absolute minimum happens to be down here. They might occur within the interval or at the endpoints, but it exists someplace. If we relax these conditions, continuity, and that the interval is closed, we start losing things. For example, if I draw a function which is not continuous on a to b, I might end up with no maximum or minimum. Because right here, this graph goes up until this point, but it actually doesn't hit this open point and it jumps down to this point. Then it begins again down here and goes up to here. It looks like the maximum and minimum should occur at these points here, but they're not actually part of the graph, so we don't consider them to be part of, we don't consider them to actually be minimum or maximum values that the function actually attains. For a value to be a minimum or maximum, the function actually needs to attain it, which doesn't happen over here. Over here, we've got a continuous function, but it's not on a closed interval, it's on an open interval. And in this case, I can have a function that, for example, goes off to infinity and negative infinity. It does not have a maximum or minimum value. Okay, so it's very important that to apply extreme value theorem, we have a continuous function on a closed interval. Okay, so here is our main criterion for figuring out where maximum and minimum values occur. This is Fermat's theorem. It says if f of x has a local minimum or maximum at x equal to c, then either the derivative is equal to 0 or the derivative does not exist. So let's look at these different possibilities. When the derivative is, if we have a function which is differentiable and has a maximum or minimum at a point, What we're saying is that the function is increasing and then stops increasing and starts decreasing at a point if it's a maximum. Well, we have to have a horizontal tangent there. Otherwise, if the tangent were, say, positive, then the function would have to keep increasing. We wouldn't have a maximum there. Same thing with a minimum. It has to be decreasing, then hit the minimum, then keep increasing, and that implies that the tangent line is going to be horizontal, have slope 0. Or we can end up with a case where the derivative does not exist. For example, something like this, something like the absolute value function. We can have a maximum or minimum if we have a sharp corner or something like that where the derivative is not defined, but that can still happen. However, we should be careful. Just because the derivative at a point is equal to 0 does not mean that there's a maximum or minimum, or similarly if the derivative does not exist. For example, if y is equal to x cubed, at 0 the derivative is equal to 0. We have a horizontal tangent. However, this is not a minimum. The function just sort of flattens out for a second and then keeps going. So you have to be careful. This does not tell you where the maximum or minimum necessarily is. It says where they could be. Okay, so these numbers that we're interested in terms of Fermat's theorem are going to be called critical numbers. So critical number C for f of x is a place where either f prime of c is 0 or does not exist. So for example, let's find the critical numbers for the function f of x is equal to x to the 3/5 times 4 minus x. So I go ahead and I take the derivative, I apply the product rule here to get that. I get a common denominator, put it together, and I end up with a derivative is equal to 12 minus 8x over 5x to the 2/5. Here it's going to be really important for us to simplify expressions because now I want to say things like when is this equal to 0? Or when does this not exist? Well, since I have a fraction, it's going to be equal to 0 precisely when the top is 0. So to find the critical numbers, we say, first of all, when is the derivative 0? The derivative is 0 when the numerator is 0, so 12 minus 8x is 0. We solve that to get 3/2. Or, when does the derivative not exist? Well, the only problem with this function, the only place it's not continuous and doesn't exist, is when the denominator is 0, when 5x to the 2/5 is equal to 0. You can solve that easily to get x is equal to 0. So, our critical numbers here are 3/2 where we have a horizontal tangent, the derivative is 0, and 0 where the derivative does not exist. Okay, so now we're ready to talk about the closed interval method. And this is how we can always maximize and minimize, in an absolute sense, a function on a closed interval. So long as f of x is continuous on the interval from a to b, closed, to find the absolute max and min, we first find the critical numbers, then we plug the critical numbers and the endpoints, which are a and b, into f of x. Whatever is the biggest value is our absolute maximum, whatever is the smallest value is our absolute minimum. So by finding the critical numbers, we're finding places where we may have an absolute maximum or minimum. Also, the absolute maximum or minimum may occur in endpoints, so we have to throw those in too. We just plug them into the function and then see what's the biggest value, what's the smallest value. Okay, as an example, let's find the absolute minimum and maximum of f of x equal to 2 cosine x plus x on the interval from 0 to 2 pi. So this is a perfectly fine continuous function on a closed interval, so we can apply the closed interval method. First, we find the critical numbers. To do that, we take the derivative of f. We get negative 2 sine of x plus 1. Okay. Some of the critical numbers happen when the derivative is equal to 0. So we set the derivative equal to 0 and we solve. Negative 2 sine x plus 1 equals 0 happens when sine of x is 1/2, which happens on this interval when x is pi over 6 or 5 pi over 6. Also, we care about critical numbers where the derivative does not exist, but negative 2 sine of x plus 1 is a perfectly fine continuous function on the entire interval. It exists everywhere, so this derivative exists everywhere. There are no other critical numbers. Second, we will make a table with our critical numbers in it, pi over 6 and 5 pi over 6, but also the endpoints of the interval we're looking at. So we want to include 0 and 2 pi. Then we plug them back into the original function. We're done with the derivative. We use the derivative to find the critical numbers. Now we're going to plug these numbers into the original function because we're concerned with minimizing and maximizing this. Okay, so I plug in 0 into 2 cosine x plus x and I get 2. When I plug in pi over 6, I get about 2.26. When I plug in 5 pi over 6, I get about 0.886. When I plug in 2 pi, I get 8.283. So the biggest value I see occurs when x is equal to 2 pi, which is 2 plus 2 pi, about 8.283. That is my absolute maximum. And the smallest value I see is this negative root 3 plus 5 pi over 6, which is about 0.886. That occurs at 5 pi over 6. So our minimum is that at 5 pi over 6. Okay, so here is an illustration of the function that we just looked at, 2 cosine of x plus x on the interval from 0 to 2 pi. And just to verify what we saw, we found that there were two critical numbers. That was at pi over 6 and 5 pi over 6. These are places where we have horizontal tangents. Now we do have a local maximum at pi over 6 and a local minimum at 5 pi over 6. However, at pi over 6, it does not translate into an absolute maximum because we have bigger values of y over to the right. But at 5 pi over 6, this is the lowest y value we get. So that's why this is indeed the absolute minimum. Now there's no place else between 0 or 2 pi where a minimum or maximum can occur because the derivative exists and is non-zero everywhere else. So the last two places we have to check are the endpoints. This endpoint has y value between these two guys, so it's not a maximum or a minimum, but this endpoint up here is clearly higher than everybody else, so we do end up having our absolute maximum right here. Okay, so here's question 1. Let f of x be x cubed minus 12x. Find the absolute maximum and minimum values on the interval from -1 to 3. Note, when you're finding the critical numbers of this guy, if a critical number lies outside of the interval from -1 to 3, then don't include it in your table. We only want the critical numbers that are actually inside this interval when we're looking for the maximum and minimum.